It did.
We're trying to solve, right? So, okay, but what's overall, how do you describe, that's correct, that's the first, good. Reverse PEMDAS, right? We're trying to isolate X, how come? Let's get rid of phones, earbuds, all that stuff, please. We're out. Only one X, good. We can isolate X because there's only a single X, okay? Good, so to do that, here's our X. We just reverse PEMDAS, so step number one would be we're going to subtract 4 from both sides. Good, so those go away. Okay, good. Now what? Oops, there's no 5 there, or no X there, sorry. Now what? Oh, I didn't, you're right. You're right.
Gosh dang it.
So what's that give us? Negative 162, good. Now what? Divide by negative 5. We cannot distribute, how come? We'd be skipping a step, good, it's being squared, so we can't distribute over a power, right? So we divide by negative 5. I wouldn't, but you could, it'd be an option. I'd still probably just divide it away, because we're really just trying to isolate the X, but it would be fine to do. But you absolutely can't here because it's being squared. Okay, so that gives us, we're getting better. Notice that the left side, we're just paring it down. So eventually we'll just have that X. And that doesn't reduce, does it? Okay, but negative over negative is positive. Okay, now what? Okay, square root, good. Now we want to undo the squared, so we're going to square root both sides. And so far so good, that undoes the squared, and now we just get a negative 2x minus 2 outside of the power is equal to, what do I have to include? Plus or minus. And we've got to simplify this, don't we? Right, we've got to take care of this. Okay, so let's do that. Let's carve out a little space here and let's simplify that square root. So if I have 162 over 5 does not reduce, so I'm stuck with it the way it is, right? We have a property that says if I have the square root of a quotient, I can separate that into the square root of the top and the square root of the bottom, right? So we'll try this first step. We're going to get the square root of 162 over the square root of 5. Square root of 5 doesn't simplify, right? 5's prime. 162, we could maybe do something with that, though. So how are we going to simplify the radical on the top?
81 and 2.
81 and 2, okay. So we could make a factor tree, and you've already got this figured out to where in our factor tree, if we can find a factor that's a perfect square, that's great. That makes life easy. So 81 and 2, and 81's a perfect square, so there's our couple, there's our single, right? So this just looks like 9 radical 2, everybody agree? Over square root of 5. Okay? All right, now what? Okay, good. Good, right here. Multiply by 1 in the form of square root of 5 divided by square root of 5. Okay, and we get what do we get on the bottom? Square root of 5 times itself is 5. On the top, we get 9 times, what's the square root of 2 times the square root of 5? The square root of 10. 2 and 5 are both prime, right? So we're not going to be able, we're stuck with that on the top. We got a 10 inside the radical that we can't do anything with. But that's a lot better than what we started with, right? We rationalized the denominator. So now instead of having an irrational number on the bottom, a square root, we've got an integer. Okay, that's good. And the top is an irrational number. It's a square root, but it's a lot smaller. Okay? So we can plug that in now. Oops. We can plug that in down here, and we can continue with our problem. So we get plus or minus 9 times the square root of 10 over 5. Okay, what are the last two steps? Okay, add 2. Where are we going to put the 2 on the right side? Good, good. So we go add 2. So those cancel. And we get negative 2x equals 2 plus or minus 9 radical 10 over 5. Last step? Good. Divide by negative 2. Okay, so our final answer then, if we divide both sides by negative 2. Now be careful with this. Our final answer is going to be x equals what? Good, because we're dividing by negative 2, so that gives us negative 1 plus or minus. Dividing by negative 2 is the same as multiplying by the reciprocal, but because we've got this plus or minus here, what are we going to do? Instead of dividing by negative 2, we're multiplying by 1 over 2, right? Okay. And so we end up with plus or minus 9 radical 10 over 10. So those are our two answers. And remember, you can't, even though it's enticing because it's on the drop-down menu, you can't enter that in Moodle as a plus or minus. You've got to do one of them, comma, the other one, right? Okay, good. If you can do that one, you can do any of them, right? All right, so I want to talk about something really cool now. This is kind of one of the honors class. We get to do a lot of different stuff in the other classes. Here's where we're going to take we're going to reroute ourselves. We're going to do a lot of stuff that a regular Algebra 2 class wouldn't really get to do. This is pretty interesting stuff. So what I want to think about here for a second is let's kind of go back and let's talk about, for a second, let's talk about the, tell you what, you got to pause for just a sec. I'm going to print something out for you. Hold that thought. Think about that. Talk with a neighbor. Remind yourselves what that's about. All right, so think about this stuff we talked about earlier. So we looked at all the subsets of the set of real numbers. I want you to think about these as filling gaps. So if we start with the natural counting numbers, right, 1, 2, 3, 4, etc., the whole numbers fill a gap, right? There's a gap there. The natural numbers don't represent the idea of nothing. And so the whole numbers come in and fill that gap, right? Whole numbers are good, 0, 1, 2, 3, 4, but they've got a gap, an obvious gap. They don't include any negatives. So we add the integers. They fill that gap. Integers seem pretty good, but obviously we're missing the numbers in between the integers, right? What about things like 1/3 or 10 halves, or 10 halves, we had that one, 10/3, something like that, right? The numbers that don't show up on the dash marks, the hash marks on a number line, which is what the integers are, right? So the rational numbers come in and fill that gap. Well, there's still a gap though, because there are some numbers, if you focus in even further, there are numbers between the fractions that can't be written as fractions. And so then we've got to include the entire set of real numbers. We add the irrationals. And we've got this seems like a complete set of numbers now. Everything we need, right? Think so? No. For sure. There's no obvious gaps there though, right? Okay, let's do another problem. Oh, frozen. It's not gonna work. Okay, let's try this problem. It's not a hard one. We can do this. So we're going to isolate x. There's a single x we can point to. We just reverse order of operations. What's our first step?
Add 4.
Add 4. So we get negative 2 times the quantity 4x plus 5 squared equals 18. now what? Divide by -2. So that's going to give me 4x plus 5 squared equals -9. Okay, now what?
Don't do it, oh yeah.
Ooh, what do we got?
Don't do it. You got a problem.
We got a problem.
Don't do it to him. Who would have saw this coming?
So we got a problem, right? We can't seem to do this. Okay, but it's got solutions. It does have solutions. They're just not solutions that we're used to. We've got to be able to deal with problems like this because their solutions are important. These kinds of things, and you might think, well, we could probably live without the square root of -9. Well, you can't. You can't. If you want to do some real-world problems, you need that. Like if you want to, for example, let's say you want to go into circuit design. You study electrical engineering, and you want to look at an analog circuit. Any analog circuit has 3 kinds of components. It's got resistors, capacitors, and inductors. Every circuit is made of that, of those 3 circuits. Now, digital circuits are a little different, but analog circuits are all made of those 3 components. But you can put those in different arrangements, and you can create lots of different things based on stereos, radios, whatever. Lots of stuff you can build, amplifiers, based on just the arrangement of those 3 components in the circuit, right? Unfortunately, you need lots of these things to build complex stuff, right? But you need to know how those circuits are going to interact. Well, the way you do that is you assign an impedance or a resistance to each of those kinds of components. But the equations that you solve to figure out what those resistances are, I mean, how much does each one resist the flow of electricity through the circuit, it depends on solutions to problems like this. So we've got to go further. We've got to push on. We've got a void here that we have to fill, right? That real numbers doesn't take care of. So we thought we had it all, but there is another void left behind. Yes, sir.
And little used for the 10 or that.
No.
Because it,
Okay, you don't anymore. I mean, when we get to up through this point, yeah, you would have put in for no real solutions. But if you remember what the wording was on all of those problems you've done up to this point, you had kind of a cop-out option, right? If it didn't work, you said, well, we put in for no real solutions. But that's specific. It says no real solutions. There's a void left for some other types of numbers that are non-real, that are outside of the set of real numbers. And so there is room for a solution, and the next level, we move down to the next section in Algebra 2, that's not going to be an option anymore, because now we're going to be wanting to know what are the actual answers based on this larger set, okay? So we got a problem here, right? We've got to do the square root of -9. What do we do? Well, we've got to extend our understanding just a little bit. We've got to look at, yeah, okay, so I'm just going to work through this problem actually, and then we'll come back and talk about how we got there, okay? So we can go further, right? What do we get on the left side? Well, we already know, I just get 4x plus 5, right? The whole point of square rooting both sides was to undo the power. So over here, this makes perfect sense. We need to have our plus or minus, don't we? Because we're square rooting both sides. But what about the square root of -9? How are we going to deal with that? The square root of -9, we're going to break it into 2 parts, right? Because it's the product of -1 and 9. So we're going to write this as the square root of 9 times the square root of -1. Square root of 9 is 3. Square root of -1? Yeah, we call it I. What is I? The square root of -1. That's what it's equal to. Okay? We call that the imaginary unit. Imaginary is a horrible word to use. I hate it. It implies somehow, here we call this one set of numbers real numbers, and we call this other set of numbers imaginary numbers. What's that make it sound like? Oh, they're just fluffy, fake things that don't mean anything. That's not true. Imaginary numbers are just as real as real numbers. They're just not used for the things that we use real numbers for. Real numbers are used for counting. Essentially, that's what they're good for, is cardinality. Imaginary numbers do all the rest of the stuff. which is most of the stuff you do in physics and engineering. So these are things that you see these things. I mean, they're never going away. They're a big part of everything we do from this point forward. And they do amazing things. You can take, just another quick example, you can do something like, you could take, if you want to build a telephoto lens, right, or some complicated system of lenses. So in physics, that's a geometric optics problem, right? So you've got all these little lens elements, and it's pretty complicated. If you ever looked inside a telephoto lens, when you zoom out and focus, there's all these little lens elements that are kind of moving in concert, and they're going left and right, and it's really a pretty amazing feat of engineering to build them. But they've all got to move in precisely the right pattern, or things are going to be out of focus, right? Or you're not going to be able to zoom in. You're not going to have that zoom in or zoom out effect. And so how do you deal with these all at once? Well, dealing with one lens is pretty simple to do. And the physics is no big deal. It's just geometric optics. But when you deal with a whole bunch of them at once, you want to be able to treat them all as one lens when you're doing your lens equations. That's how you do it. You can build you can collect a whole bunch of individual lenses into one sort of, you can treat it as one single lens if you just use complex numbers, complex analysis. It shows up all the time. In fields and waves, talking about electricity and magnetism, everything is, that's all you see. Every equation you look at is going to have eyes in it. So it doesn't go away. I mean, we're going to see more and more of this stuff. It's a little bit strange, but this really is an important number. If we just do that one little thing, this equation becomes easy to solve, right? So we end up on the right side with plus or minus 3i. Okay, now what? Subtract 5. Okay, so we get 4x equals negative 5 plus or minus 3i, and then finally divide by 4. We'll apply the same rule we did in the last problem here, because even though 3 is rational, there's no square roots, we obviously can't combine a negative 5 and a 3i. They're different kinds of numbers, aren't they? So these aren't going to combine, and so we'll just divide each term separately by 4. We won't have a common denominator, right? And we end up with the answer, x equals negative 5/4 plus or minus 3/4 I. So we get two different answers out of this, right? We get one solution is x equals negative 5/4 plus 3/4 I, or x equals negative 5/4 minus 3/4 I. Those might look strange, but those are completely regular looking complex numbers. Complex numbers, I'll come back to that slide in just a second, that's pretty cool. Complex numbers, this is how we write them. This is the standard form for a complex number. We call, like we would say z, for some reason z is the variable we use to represent a complex number. And some complex number z is just written as a plus b times I. We say that this part over here, the a is what we call the real part, and the b times I is called the imaginary part. Okay? We try to organize our thinking with these complex numbers a little bit. We want to, if we're going to write all complex numbers in this form, we want to be able to integrate these complex numbers into this, right? Into this set diagram that previously everything we knew was right there. Now we got to account for these new complex numbers. So we can make it look like this, right? We add these other sets. We say that the set of all numbers is the set of complex numbers, and the set of real numbers is really just a subset of that. The set of real numbers is the set of complex numbers where there is no imaginary part. So what must the value of b be? 0. 0 times I is 0. 0 times anything is 0. So the set of complex numbers where b is equal to 0, where the imaginary part disappears, that's what we now understand to be real numbers, right? They're all of the form a plus 0 times I. Well, we don't write 0 times I. That's just 0, right? Okay, but all the other numbers where b is not equal to 0, We need a place to put those, so they go over here. Well, there are things called pure imaginary numbers. What do you think a pure imaginary number is? Doesn't have any real part. So what would A be equal to? 0. So if in a complex number A is equal to 0, then that puts it into the set we call pure imaginaries. Okay? But most, like a normal number now to us, from this point forward, is going to be a number that has both an imaginary and a real part, and so A and B would both be non-zero. Okay? One way to represent these that's really effective is in what we call the complex plane. It's kind of blurry. I'll just draw. So here's the complex plane. So in the complex plane, we're going to map complex numbers into two different axes that are at right angles to each other. So we'll say, later on in calculus, we'll say they're orthogonal. They're at right angles. So this is what we call the real axis. And this is what we call the imaginary axis. So if we were to take the number, for example, what if we take z equals, let's say it's 4 plus 3i, where do you think we would plot that in the complex plane?
3i on the imaginary axis, 4 on the real axis.
Okay, so it's going to be, we just think of it like an ordered pair, right? So the real axis, really what we're looking at here, we're charting the value of A. And on the imaginary axis, we're plotting the value of B, okay? The complex, the imaginary coefficient. And so this would be over 4 and up 3. So there's the point with coordinates 4, 3 corresponding to that complex number. Okay? Now, a lot of times, it's useful to, we can think of that as just a point on the plane, that's fine. A lot of times, we'll think of that as a vector. And vectors, we haven't really talked a lot about vectors, it's no big deal. I mean, they sound really complicated, they're not. All a vector is just, think of it as an arrow that starts at the origin and ends at that point. Okay? So, the length of that vector is useful. The length of that vector, we call that, it looks like we're saying absolute value. What that actually means is the modulus. Okay, it's the word we use in math. Just means the length. Okay? How do we find the length of that vector? If it's starting at 0, 0 and ending at 4, 3. It's just distance formula, exactly. It's just distance formula, isn't it? Right? So it's just going to be the modulus of z is just equal to the square root of a squared, right? Because that's a, isn't it? Plus b squared, right? So what is it for our number up here then? For us, the modulus of z is the square root of what? 4 squared plus 3 squared. What's 4 squared plus 3 squared? 25. Square root of 25 is? So that's the modulus. That's important. Okay, that's important. A lot of times, like in engineering, the modulus is the thing that has the real physical importance. Okay? Okay, so these are pretty amazing. There's something that, here's kind of, I'll just spend just a second on this. This is what we call the Mandelbrot set. The Mandelbrot set is based on iteration and iterations done in the complex plane. And I'll explain it in more detail after you've had a chance to work with these complex numbers a little bit, practice with them. But the Mandelbrot set is pretty amazing. It has infinite complexity. So it looks like, well, it looks like kind of fancy, kind of, I don't know what those things are, kind of little hairy edge on it or something. But if you focus in on it, like if we picked a point, like let's say right there, and we just zoom in and zoom in and zoom in, what happens? It's completely self-similar, which means that as you zoom in and zoom in, those little pieces up there look exactly like this, right? And as you zoom in and zoom in and zoom in some more on the edge, you just keep getting the same repetitive characteristics. So that's what we call, and this, this isn't like anything we tested on, it's interesting. That's what we call a fractal. So a fractal is something that is self-similar on any dimension. And fractals they actually play an important role in real life. I mean, you can see them all around you. If you look at something like a snowflake, if you focus in on a snowflake, you'll see that the more you focus in, the more it looks the same. The crystal structure is the same everywhere. Even if you look at something like a tree, think about a tree. From a distance, you can see it's got a trunk and some branches. You focus in on a branch, and all of a sudden the branch looks like the trunk, and it's got more branches. Focus in on one of those smaller ones, and then it still branches out even more and more and more. Now, it doesn't go infinitely far with the tree, but you can go through many iterations of that. And so in mathematics, we can even say things like there's a fractal number we can assign to a tree. And you can categorize things in the world based on their fractal number. How self-similar are they? Things that are more self-similar have lots of things in common, geometrically, and it turns out even physically. Even just the way that water is transported in trees can be shown to correlate to how self-similar they are. So these bizarre things in math that just seem like they're out of the blue, they really do have profound consequences in understanding the world. You can look at things like a mountain range. Think about a mountain range. From a distance, it looks pretty jagged. Well, you get closer, and there's a ridge line. Well, the ridge looks kind of jagged. Get even closer, and there's just a rock formation on the ridge. Same kind of jags in it. Get closer, there's individual rock. You see what I'm getting at. The closer you get, you see that it's essentially the same kind of pattern. So we call that, once again, that's what we call a fractal. And the study of that is called fractal geometry. I'm going to show you guys a video at some point. It's kind of interesting. It talks about how one application that you'd be kind of glad exists is when you're playing all these stupid video games, like Fortnite and all this nonsense. They utilize this because the computational power that would be required, like if you're making a movie, say you're making a big Star Wars movie or something, the computational power that would be required to like artificially generate forests on hills and things, it's astounding. You couldn't do it, right? There's no computer in the world that could generate that kind of detail and have a frame rate that's gonna look anything but dorky, right? To have it actually look like a real life thing, there has to be a way that these computers can build this scenery to look realistic. Well, what do? That. All you have to do is set up a really simple fractal pattern where you can say, if you're in a forest, then here's the relationship between the pixels. Trunks go up and things branch out. That's a pretty simple set of instructions for a computer to follow, and it can fill a bunch of space by making lots of trees that look like a forest by just following that one simple pattern instead of having to figure out exactly where each pixel is going to go in a forest, right? And so you can cut down by orders of like 1 billion. You can cut down the number of operations that have to be done to create this artificial scenery. So once again, there's all this stuff that goes along with this. What are we talking about? Just filling a void in the set of numbers, and it leads to all this other stuff that you would never expect. And that's the way math and science oftentimes works. You open a door, you don't know where it's going, and all of a sudden you got all these profound applications that you never even realized existed. Okay, when are we out of here?
25.
25, okay, so next step. So let's actually do something with these things. Oops. Okay, so, we'll get all that stuff. So let's just practice like adding other things, really simple. So if we wanted, we got to go back to basics though. We got this new set of complex numbers. We want to start off by learning how to do arithmetic with the complex numbers. So I've got, let's call this Z1 equals 3 plus 4i, Z2 equals -2 minus 5i. What is Z1 plus Z2? What do you think? And you're going to be right. What is it?
1 minus 1.
Yeah. How'd we get that? You're just adding like terms, really, aren't you? You're just adding the real parts and the imaginary parts. Make sense? So -3 plus -2 combines to 1. (4i) plus -5i combines to -i, right? Adding is super simple. I mean, there's nothing to it. What about subtracting? Almost as easy. What if we do 3 plus 7i minus the complex number -2 minus 4i? Okay, so what are we going to do? What would the steps be maybe to solve this? Distribute, right. So you get a sense that we're just treating the I like a variable. It's not a variable, but it acts just like a variable because it separates the real terms from the imaginary terms, right? So we distribute the negative, and we get 3 plus 7i plus 2i plus, plus 2. Plus 2 plus 4i, so let's add like terms. 3 plus 2 is 5, 7i plus 4i is, bingo. Okay. What about something like this? What if we have 3 times 2 minus 11i? What's that equal to? Oh, sorry. 33. Can't. Okay? Easy. Okay, this is a little tougher though. You're gonna have to take it one more step with this now. So what if we have something instead, like what if we do a product of complex numbers, where they both have both real and imaginary parts. So say we do 5 plus 6i times -3 plus 2i. Okay, so yeah, we could just FOIL this. We're just gonna, and all FOIL is just distribute, right? That's all we're doing. So we can distribute the terms in the first quantity over the terms in the second, how about? So if we distribute the 5, what are we gonna get? -15 plus 10i. If we distribute the 6i, we're gonna get -18i. What's the last one gonna be? Okay, what about that?
Is it -1?
It is. How'd you get that?
Because I is radical.
Okay, good. So if we define I as the square root of -1, let's make a list here. What's I squared going to equal? Yeah, if I square a square root, I'm just undoing the square root part, right? So I squared is -1. Let's keep going. What's I cubed? -I, right? I cubed is the same thing as just I squared times I. Everybody agree? So I'm just getting -1 times I, so that's -I. How about I to the 4th?
1.
Yeah, right? The most convenient way to think about that isn't I to the 4th. Think about your properties of exponents that we reviewed. I to the 4th is the same thing as I squared, right? That's a convenient way to break that up. So I squared squared, I squared is -1, squared is +1. Okay. What is I to the 97? I'm serious. What is I to the 97? It's -1. You're right. How'd you get that? Actually, hold on. No, it's not.
Oh, it's good, yep.
No? Sorry. Yeah. Yeah, you see, this is just gonna keep, we're just gonna keep repeating in cycles of 4, aren't we? Now, let's look at this. right? That's right. So wouldn't I to the fifth, if I were to keep going with this, I to the fifth is the same thing as I to the fourth times I, right? I to the fourth is just 1, right? So that just roots us back to the first step in the next sequence of 4. It's going to keep doing that infinitely, right? So I to the 8th would be the same thing as I to the 4th squared. Well, I to the 4th is 1, right? So every multiple of 4 is just going to give us back 1. And then as we increase, add to that, so a multiple of 4 plus 1 is going to give us that, right? Talking about the powers here, the exponents, right? If the exponent's a multiple of 4 plus 2, we go there. Multiple of 4 plus 3, we go there. So 97, 4 goes into 97. Well, what's the multiple of 4 nearest to 97, below 97? 96. So that's the same thing as I to the 96 times I, right? Well, that's 1 times I, right? See how that works? Okay? Well, that's probably good for a day, huh?
Yeah, definitely. I don't know, lazy or something, right?
Yeah.
I'm gonna take 2 of these and go
Sure.
outside.
Sure. Okay.